Before smartphones, there was little interest in mobile wireless broadband. Mobile operators only had to carry voice signals, and a low data rate of 8 to 10 kilobits per second was more than enough for that. So from 1G to 3G, operators focused instead on improving their economics by increasing how many calls can be made within a particular cell with the same amount of spectrum. Then, in the mid-2000s, came the smartphone, which turned wireless broadband into a real customer demand, which meant drastically raising data transfer rates. But how are operators going to do that without buying vast sums of bandwidth or pumping huge amounts of power into the signal? What the industry devised and adopted was deviously clever. In this video, the story of multiple input, multiple output, or MIMO. Let us start with a familiar thought experiment. Imagine me and you together in a large room. I shout hello at you. The sound wave emanating from me can take different paths towards you. One wave might go directly from me to you in a simple straight path, but a different wave might go towards the floor, another to the ceiling, yet another to the walls. These obstacles reflect, diffract, or scatter the sound waves. The paths are also all of different directions. So the end result is that when you receive my hello, you receive it at random different times and at random varying strengths. This is known as multipath propagation, and you might be familiar with the sound wave version of it, an echo. But radio waves experience something similar, and it can cause problems. Cellular signals are carried by radio waves, and the data encoded into the waves via peaks and valleys. Multipath propagation causes the same cellular radio waves to be received at different times. If the peaks and valleys do not match up well enough, then they might cancel each other out, causing something called destructive interference. If that destructive interference is too strong, then we cannot recover the encoded bits and lose that information. And sometimes, if the delays of the various multipaths are long enough, then they can interfere with other data signals arriving at the same time, causing serious distortion. Remember those old analog televisions with those rabbit ear antennas we adjusted? Sometimes you might see extra outlines or echoes of images. This is ghosting, unrelated to the ghosting of online relations, and it can happen because of multipath. One long-standing way to deal with this has been to deploy multiple antennas. This means to set up multiple receiving antennas to try and catch independently fading copies of the same signal. You can select the copy with the strongest signal, or better yet, merge them together. This technique is known as selection diversity and dates all the way back to the early 1900s when Marconi himself was establishing a commercial wireless transmission service across the Atlantic. In the days before DeForest's vacuum tubes, there was no true way to amplify signals, so the transatlantic signals were pathetically weak. But Marconi discovered that adding a second reception antenna let him take advantage of multipath propagation to find the best signal. So the idea of sending to multiple receiving antennas to reduce interference has been around for a long time. But what about the reverse? How about we use multiple transmitting antennas to send data to a single receiving antenna? So if the signal from one transmit antenna fades, then the transmitter knows to switch to the other transmit antenna. However, this was not as easy to implement at the start because the receiver needed to somehow tell the transmitter which one of their transmitting antennas is the good one, and that is inconvenient. It was not until the 1990s that Dr. Armin Wittneben of Switzerland first proposed a new way to deliver this feedback without explicitly needing to transmit it. This scheme was then refined by Siavash Alamuti. He proposed a brilliant coding scheme where the two transmitting antennas first send one straight copy of the data, and then they send a swapped and tweaked second copy of the data. The receiver can then combine and unscramble them with simple math. Quite clever. The Alamuti scheme and others like it are called space-time coding, and over the years, the topic has attracted tens of thousands of research papers, though I think it is kind of funny that 5G today uses just a simple space-time coding scheme called cyclic delay diversity. Just send the same data from the antennas, but with a slight time delay. One transmitting antenna to multiple receiving antennas is the next arrangement to talk about. Another early concept implementing this is Space Division Multiple Access, or SDMA, a channel access method. Today, it's called multi-user. Multi-user divided up spectrum users inside a cell by their physical locations. We form targeted radio beams so that we can transmit and receive signals from two users inside the same cell with as little interference as possible. In 1992, a company called Arraycom was spun off from Stanford to commercialize multi-user, co-founded by Richard Roy, Motorola cell phone legend Marty Cooper, and a fellow named Arogaswamy Palraj, who we shall mention more later. Arraycom worked on smart antennas to produce targeted beams that can even follow people around. The idea had potential. It was integrated into the Japanese PHS handyphone system in the 1990s, but suffered implementation problems. Pairing the base stations and handset was tricky, and if the handset moved around, even slowly, then its pairing had to be recalibrated. Arraycom eventually pivoted to doing 4G and 5G software, which worked very well for them in the end. Up until now, these antenna diversity schemes focused on reducing interference or increasing capacity inside a cell. But there was another benefit, and that was first tapped by the aforementioned Arogaswamy Palraj. Palraj was born in India. He joined the Indian Navy and spent 20 years there working on advanced surface ship sonar technologies. He founded 3 national labs there working on AI, robotics, and military electronics. In the mid-1980s, he went to Stanford University as a visiting scholar. There, he worked on an algorithm called Esprit, which can be used for estimating signal parameters like frequencies. In the early 1990s, he decided to go into academia and returned to Stanford as a research associate at the bottom of the ladder. There, he joined a project led by his colleague, Professor Gene Golub. Funded by the Air Force, the project studied ways to separate mutually interfering signals arriving from different directions. This often happens for a signal sent out from a traveling aircraft in the sky. To test out these algorithms, he built an outdoors experiment with 2 cordless phones. Outdoors, the experiments found that the 2 phones' signals were separable with distance in between them. When they got close together, then the signals were no longer separable. This all made sense. But during a rainy day, he and some other students had to bring the experiment indoors. A student carried those 2 cordless phones inside in one hand. Whilst doing that, Palraj noticed that the setup was still separating the 2 phones' signals, despite the 2 devices being literally in the same hand next to each other. At first, it didn't make sense, but Palraj quickly realized it was because of Multipath and moved on, knowing that DARPA, the sponsor of the experiment, wouldn't care about this. It was only a few days later, whilst getting a haircut, that Palraj realized that Multipath can be used to directly increase data transmission capacity, a new twist. A few years later, he and his supervisor Thomas Callith filed a patent titled Increasing Capacity in Wireless Broadcast Systems Using Distributed Transmission Directional Reception. That patent was granted in 1994, and today it is considered the foundational basis patent for MIMO. MIMO is so wickedly brilliant because it turns what before has been a weakness, multipath propagation, into a strength to vastly increase the data rate of a wireless link. Let us first imagine a simple wireless connection, one antenna on the base station sending a wireless data stream to one antenna in the handset. We call this single input, single output, SISO. With this, data flows in just a single dimension, time. Bits are sent like how we speak words in a sentence, in a sequence with one coming after the other. A SISO's maximum capacity bitrate, which I shall call K, can be calculated using the Shannon capacity formula. K equals B times log base 2 of 1 plus G, where B is bandwidth and G is the received signal to noise ratio. So, per Shannon, raising K means raising either bandwidth or the signal-to-noise ratio. But raising the bandwidth means buying more spectrum, and spectrum is finite, expensive, government license, expensive, and expensive. It is also expensive. Okay, then, how about raising the signal-to-noise ratio, or SNR? A higher ratio means that it is easier for the receiver to grasp signal over the noise. Ramping SNR is most easily done by ramping the signal's transmitted power, but mobile phones are power constrained, and safety laws restrict phones to a max transit power of 0.25 watts anyway. Another thing, the two factors are interconnected. Raising one makes raising the other harder. I will get back to that later. So MIMO scales data capacity by adding a second new dimension, space. We can increase capacity without increasing bandwidth or power by adding more transmitting and receiving antennas. Here is a general idea of how it works. The most common MIMO setup has 4 layers, meaning that there are 4 transmitting and receiving antennas on each side, but there can be more and less. We take a data signal that is 4 times some K capacity bitrate. We split or demux that signal into 4 substreams of K bitrate each. Then we can transmit each substream with one of the 4 antennae, all on the same bandwidth, but at 1/4 of the power. But wouldn't that all these streams cause interference? Au contraire, thanks to multipath propagation, each of the 4 transmitted signals take different paths to the 4 receiving antennas, so they arrive with slightly different loudness, quote unquote, and timing. The end result picked up by the antennas will be a bit jumbled, but thanks to a special set of sounding signals, the receiver can discern a fingerprint of how signals travel from each transmitting antenna to each receiving antenna. Using this, each of the 4 receiving antennas can filter out the other 3 signal streams to get only the one they need. Once all that is done, all 4 substreams are recombined together again like Humpty Dumpty. Early on, nobody believed that the technology could possibly deliver the gains it said it would, and for good reason. Let us look at a typical 5G link in a typical urban environment. Such a link has a channel bandwidth of 20 MHz and an SNR of 24 dB. Using this, a standard 1x1 CISO link gets you a Shannon capacity data rate of 160 megabits per second, but a 4x4 MIMO system gets you 640 megabits per second. Though to note, the Shannon data rate is a theoretical maximum. Real-world data rates will be substantially lower. What does it take to achieve 640 megabits per second without MIMO? It would require a wildly impractical increase of the signal-to-noise ratio by 16 million times, which corresponds to a transmit power of 2.56 gigawatts. And as for bandwidth, it would require over 4 times more bandwidth because, as I hinted before, raising the bandwidth hurts signal-to-noise ratio, which in turn needs yet more bandwidth to compensate. Skip a bunch of math, and you need 6 times more bandwidth, not 4, for a CISO to match a 4x4 MIMO setup, and that's expensive. Stanford's Office of Technology Licensing seemed to recognize the significance of such an invention. When publicizing most patents they want to license out, they do a simple press release. With this one, they set up a dinner and workshop to promote it. But people were skeptical that something as simple as adding a few antennas can create such massive bitrate capacity gains. They thought there was a mistake in the math or the experiment. Paul Raj also then, having no established background in wireless, did not help either. As Paul Raj's group at Stanford tried to get people to adopt MIMO, 2 Bell Labs researchers were working towards the concept as well. In the early 1990s, a soft-spoken but brilliant researcher from New Jersey named Gerard Jerry Faschini was asked to explore the fundamental limits of bitrate transmission, to learn what is the greatest number of bits per second that can be sent over a medium. Faschini recalls in an oral history that he began by studying antennas, trying to build the best possible antenna, and he asked a colleague, Mike Gans, for help. Gans suggested that you should not visualize it as a single monolithic antenna, but rather a collection of smaller, simpler antenna elements. This major insight led Faschini to a circuit with multiple antenna inputs, leading to multiple antenna outputs. Foschini recognized this from circuit theory as a MIMO, which back then described a circuit with multiple inputs and multiple outputs. The theoretical equations for such MIMO circuits have been known since the 1950s, but with those circuits, the connections are wired, known, and fixed, not like wireless with its scattering and random multipaths. But after Foschini adapted those equations to the wireless situation the best way he could, he plotted the results and saw the same thing Paul Raj saw, that adding more antennas dramatically increased capacity. In 1998, he and Gans published an influential paper called On Limits of Wireless Communications in a Fading Environment When Using Multiple Antennas, discussing MIMO's performance value. Foschini and Gans were clearly not aware of Paul Raj's MIMO demonstration experiments, doing their work independently, but abstracting the MIMO channel into equations that elegantly proved its performance superiority helped win over academia and industry. Bell Labs' team also publicized some products. This included the Bell Labs layered spacetime algorithm, BLAST, an architectural framework for detecting and parsing the signals received from multiple antennas via Multipath without knowing the details of the scattering environment. BLAST evolved into VBLAST, a more practical architecture for implementing MIMO's multiple antennas. Bell Labs also announced that they had fabricated a prototype chip implementing the BLAST architecture, showing that it was possible to transmit up to 19.2 megabits per second over a 3G wireless network. Deciding that he had to demonstrate the technology's use in the real world, Paul Raj founded the first MIMO commercial startup in 1998/1999, Gigabit Wireless or Iospan Wireless. Iospan developed wireless broadband technology to provide fixed wireless access to city and residential customers. They chose that market for two reasons. First, mobile chips in the late 1990s did not yet have the compute capacity to implement MIMO. And second, getting into the global cellular standard would have taken immense resources that only an established company like Qualcomm would have. But with fixed wireless, you can focus on selling it to one city and one group at a time. Iospan's work led them to put MIMO together with OFDM. OFDM refers to orthogonal frequency division multiplexing. Invented by R.W. Chang of Bell Labs in 1957, it is a way of dividing spectrum for multiple users to share, like TDMA or CDMA. MIMO and OFDM are wonderfully complementary. OFDM slices up spectrum for multiple users in a way that is optimal for scaling up the number of antennas, and MIMO helps us make the most of each slice for each user capacity-wise. Iospan raised over $70 million from investors like Axel Partners and built a full fixed wireless network in 2001. But unfortunately, the market had not yet developed. After the dot-com crash, Intel bought out some of the company's assets in 2003. Intel and its CTO Pat Gelsinger strongly believed in MIMO's potential to challenge copper and the established wired telecom networks. Implementing MIMO OFDM for mobile requires intense computation, as I mentioned earlier, and Intel saw that as being right up their alley. Intel merged Iospan's technology into a mobile broadband standard they had been working on called WiMAX. They then invested $7 billion into championing WiMAX against LTE, championed by the 3GPP Mobile Telecommunications Standards Group. But 3GPP responded by integrating MIMO into their own 3G WCDMA standard, aping many of WiMAX's strengths while also providing backwards compatibility for telecom operators. In 2007, 3GPP released their 3.75G standard HSPA+. Before that, HSBA networks offered 3.6 to 7.2 megabits per second. MIMO dramatically boosted that up to 28 megabits per second. LTE arrived with the following release in late 2008, adopting both MIMO and OFDM. The results were, of course, revolutionary. MIMO also revolutionized wireless home networking, and Wi-Fi in particular. In the early 2000s, Wi-Fi showed promise, but the technology still had to get better than wired. The latest standard, 802.11g, reached data rates of just 54 megabits per second, far short of the 100 megabits offered by wired Ethernet. So early Wi-Fi semiconductor companies like Atheros and Ergo urged the IEEE, which governed the Wi-Fi standard, to adopt MIMO. And in the mid-2000s, they worked MIMO OFDM into their third generation of consumer-oriented Wi-Fi standards called 802.11n or Wi-Fi 4. The 802.11n standard supported up to 4 antennas to raise data capacity limits from 54 megabits per second to as much as 600 megabits when equipped with the 4 antennas. Interestingly enough, bureaucratic squabbling delayed the standard's release for a few years. In 2005, Wi-Fi router makers Belkin and Netgear jumped the line by releasing what they called Pre-N. With Pre-N, you got speeds of up to 108 megabits per second, but only if you use their whole proprietary system. Not sure how well it sold. Nevertheless, between the 4G LTE and Wi-Fi standards, MIMO had won the wireless world. By the end of 2024, 90% of the world's population received data via a MIMO-enabled technology. MIMO continues to evolve even into today and has since incorporated various new features. Let me run down a few of them. One is polarization. Radio waves can be polarized, linear, circular, or similar, and the current wireless standards have incorporated linear polarization dimensions into the MIMO antennas to add more layers and enhance performance. They have gone to higher frequency bands, which presents interesting opportunities. Higher bands mean smaller wavelengths, which mean physically smaller antennas. But smaller antennas have less power per antenna, so to maintain previous power levels, engineers bundle 500 to even 1,000 tiny antennas together into a single array. They are calling this massive MIMO, and with it, they can form narrow beams to users like the aforementioned multi-user did. I probably wouldn't call it massive, however, since we're still using the same number of MIMO layers, 3 to 8. Beam MIMO is probably the more accurate term. Another development has been line-of-sight MIMO. What happens when the antennas are in sight of one another, with no obstacles to make multipaths? Line-of-sight MIMO works on this by having the antennas transmit and receive at spaced multiple wavelengths apart. I want to thank an anonymous expert on MIMO for taking the time to speak with me and walk with me through this rather complicated topic. MIMO is an idea that took years to come about and find its footing, but thanks to the hard work of many brilliant people over the years, it will forever be cemented into the world's wireless standards. Today, Google Scholar notes that there are over 450,000 research papers on MIMO and over 570,000 patent publications on it, active, expired, in process across all jurisdictions. So, I want to applaud this wickedly devious concept, MIMO, and how it so brilliantly turned a weakness into a strength. Our modern cell phones suck down gigabytes of data each day, and MIMO makes it possible. The work stands as a monument to human technological ingenuity and cleverness. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.